So, elementary functions of complex variables. So when we talk about elementary functions, we mean things like trig functions, hyperbolic functions, and log. So we can actually define what we mean by cos, sine, cosh, and sine of a complex variable using these formulae here. The hyperbolic functions, well, the definition is really the same as for real variables. For the trig functions, you probably haven't seen them defined in this way, but actually it's fairly obvious this is going to work because we know that from the Euler formula, e to the iz is cos z plus I sine z, and e to the minus iz is going to be cos minus z, which is the same as cos z minus, well, plus I sine of minus z, and sine is an odd function, so the imaginary bits cancel out. You get two lots of cos and you divide by 2 and you get cos z. Similarly for sine z, you can easily check that that formula works. The remaining trig and hyperbolic functions you just define as you would expect to define them. Now you know what sine and cos are, you just get tan, cot, sec, and cosec in the same way. Hyperbolic functions defined in the same way. You might not have seen functions like shek before. In case you don't know how to pronounce them, people pronounce tan with a hyperbolic tan function. No one says hyperbolic tan or tan hyperbolic, even worse. You either say tanch or fan. Then you've got koth, shek, people say rather than sech, shek, and koshek. Out of these functions, you might like to think which are physically the most useful, and why would a function be physically most useful? Well, a function which is physically useful is one which doesn't have an infinite value anywhere. So obviously tan has an infinite value when, for example, z is pi by 2. Sec has an infinite value when z is 0 because it's 1 over cos. Sorry, got that wrong. I'm talking about cosec has an infinite value when z equals 0. Cos is 0 when z is pi by 2. So the sec has an infinite value when z is pi by 2. Well, the answer to my question is actually tanch and shek are actually nicely behaved functions from the physical point of view because they don't go to infinity anywhere. Tanch always lies between -1 and +1, and shek lies between 0 and 1. So the trig and hyperbolic functions are actually related to each other if we consider complex variables. This is fairly easy to see. All you have to do is replace z by iz in these formulae. So obviously if you replace this z by iz, so cosh iz gives you e to the iz plus e to the minus iz over 2, but that's precisely what cos z is. Similarly, if you replace z here by iz, then what you get, well, the z here the iz here turns into I times iz, so it's e to the minus z, and the z here you get e to the plus z. So this is actually just cosh of z. Okay, so cos iz is equal to cosh z, and cosh iz equals cos z. Okay, so they're easy to remember. That's those two dealt with. Sorry, the first two dealt with. Then same with sine and shine. Then you get this extra factor of I coming in. Again, that's fairly straightforward to see. If you've got shine of iz, then you're going to get i's here, but you haven't quite got sine z. You need to divide by I to get sine z. That means I times sine iz is equal to sine z. Sorry, is that what I said? Yeah. Okay, so all of the usual identities that you know from real variables still work for complex variables. So cos squared plus sine squared is equal to 1. Cos squared minus sine squared is equal to 1. Cos is an even function, cos is an even function, doesn't matter whether z is real or complex, it still works. Similarly, sine and sine are both odd functions. This result here still works for any z. And also the sum formulae work. Well, to prove all of these, it's a bit tedious to do, but you can actually just use the definition again to check they all work. Now, something you may have noticed or may not have noticed before is that there's something similar about the trig function and the hyperbolic function identities. In a way, this is not really surprising, given that cos and cosh and sine and shine are so closely related. So if you look, here you've got cos squared plus sine squared, cosh squared minus sine squared. With these, you've got cos z1 plus z2 is cos minus sine, but with the hyperbolic functions, you've got a plus here. With the sine of z1 plus z2, you've got sine cos plus cos sine. Shine looks the same. You've got shine cosh plus cosh sine. So sometimes sometimes the signs agree with each other, and sometimes they don't. Okay, so here they don't. You've got a minus here you've got a plus, and here you've got a plus here. So what's the difference? Well, the rule is actually known as Osborne's rule, and it basically says that whenever you have, if you want to change from one identity to the other, if you have two lots of sines multiplied together, so you've got sine squared here, or sine times sine here, then you need to change the sign, the S-I-G-N, in front of those two signs multiplied together to get the hyperbolic equivalent. Otherwise you don't. In fact, it's a product of two signs, or 3 or 6 or 7. But normally you just see it with two signs and identities like this. I'll leave it as something you can try to see why that is, but I've given you a bit of a hint about how you can show that. Now 1.127 is not an amazingly convenient way of okay, I mean, for example, say you wanted to calculate cos of 1 plus I, for example. Okay, you could use this formula and substitute it in, but it's actually a bit of work, and it's actually more efficient to use these formulae instead. So z we're writing as x plus iy. So supposing you want to calculate cos of 1 plus iy, well, this gives you the formula directly in terms of trig and hyperbolic. You don't have to bother with this exponential stuff. And so if you actually want to calculate cos of 1 plus I, well, x is 1, y is 1. So the answer is cos 1, cosh 1 minus I sine 1, shine 1. And you can work out those numbers. To show that, you can just use these formulae here, where you put z1 is x and z2 is iy. Just plug those in and you get these results here. So one thing I might not have mentioned now yet is that with complex variables, well, once you've introduced complex numbers, things that you thought were impossible to answer, such as things that your calculator gives you errors. So, for example, if you put inverse cos of 2, then your calculator will give you an error, and you might think, oh, there's no such thing as inverse cos of 2. Well, it turns out there is. It's just a complex number, and basically, complex numbers allow you to answer any question in terms of functions. So if you want, well, obviously you get the answer to square root of negative numbers, but anything you try, you might sort of raise a complex number to the power of a complex number. Well, the answer is still a complex number. You can't get outside of complex numbers by doing arithmetical operations. So in this next example, what I'm leading up to is that actually these are quite convenient for finding inverse cos of strange things like 2. So in this next example, we'll see how that works. So if cos of z equals 2, we want to find z now. Okay, so from this, we know that this, well, we're saying cos z equals 2. What is z? Okay, so we take real parts and we say, okay, therefore 2 is equal to this, because this has to be real. And the imaginary part, well, the imaginary part has to be 0, because 2 has 0 imaginary parts. So that means this thing here has to be 0. Okay, so that's what we've got here. Cos x cos y is 2, sine sin x sin y is 0. Now, what do we know? We know that we can't possibly get 2 here with... Okay, we know we can't get 2 with a real z, right? So z has to be complex, which means that y can't be 0. Now, if y is not 0, in order to get this to be 0, it means that sine x must be 0, which means that x is equal to n pi. Now, if we put x equals n pi into here, we get minus to the power n. That's a useful thing to know. Cos of n pi is minus 1 to the power n. Cosh is always positive for real y, so that means that we know that n has to be an even number. So I'm going to write n equals 2m in our final answer, and that just leaves us with, and therefore this is going to be 1, and that just leaves us with y as in inverse cosh 2. So our final answer then is z is equal to x plus iy. X is 2m pi, as we've said, and y is inverse cosh of 2, which can be plus or minus cosh of... cosh is an even function, so it has 2 possible inverses. So you can now do question 4, and I'm actually limited to 15 minutes with this program for videos, so I think I'm not going to quite manage to do the next bit. Okay, so we'll stop there for the time being.